here today we have Holger Vömel, close, who's at Lindenberg at the Meteorological Observatory. Holger got his four diplom in physics from the University of Frankfurt. Then went to University of Heidelberg, got a diploma in physics, and then came to Boulder to get a PhD in chemical physics from the University of Colorado. I guess he stayed in Boulder for a while. His topic was using in situ measurements of water vapor using a balloon-borne frost point hygrometer, and I guess a lot of that was motivated by ozone research to get the humidity environment. So he stayed working at Ceres and Payos here in Boulder, working on ozone research, got into other chemistry, chlorine and bromine, and then is now at the senior scientist and head of the GRUAN Lead Center, and will be telling us today about about soundings. So thanks.
Okay. Thank you. It's nice to have a good crowd here. So I'm going to give a little bit of a mixed bag here. It was very interesting to put this talk together because I want to serve a lot of needs and a lot of customers. And suddenly I thought, well, you know what? There's a lot of great stuff coming out of soundings. And of course, a lot of sounding history here. So I thought I'd start out with a little bit of real in situ sounding history. Of course, humans got up in the air in 1789 or something like that, in the late 1700s on hot air balloons. But it took maybe, shall we work in there? It took maybe another 100 years or so till people actually really got the hang of it to use balloons for atmospheric observations. And of course, those were not small balloons. Those were hot air balloons or gas balloons, or even combination of hot air and gas, which they had back then, to do vertical profiling of it. Of course, those were major activities. That actually is what today would be called a selfie. So this is Alfred Burson and Hans Klein. Alfred Burson, he was a meteorologist who actually later also worked in Lindenberg. I say a little bit more about that. And he was one of those people who actually liked going up in balloons and taking measurements from that. That particular balloon was actually financed by the Emperor of Germany personally, and is one of three of those big balloons that they had over the time to do this sort of observations. The real big guys in upper air observations, a little over 100 years ago, I put up here Abbott Lawrence Rotch. Here in the US, he founded the Blue Hill Observatory right outside of Boston. And he started basically with regular observations of upper air parameters. Upper air back then was largely the lower to middle troposphere, just the lower few kilometers. And to do that, he used kites. Richard Assmann, he is the founder of Lindenberg Observatory, so it's actually a place with quite a lot of history. And he is the co-discoverer of the stratosphere. The other co-discoverer is Léon Philippe Tesserand de Bourg, and the founder of the French Observatory at Trappes, right outside of Paris. Interesting enough, Abbott Lawrence Rotch and Tesserand de Bourg, they founded their observatories with their own personal money. They had no government support whatsoever. They were independently wealthy. Of course, very quickly it was realized, this is a really cool stuff that they did. So they got roped into the Met services or the predecessors of their time. Richard Assmann, he had full support actually of the German government. As I said, Kaiser Wilhelm personally financed some of the activities. I'll show the next slide. One of the interesting things I want to point out, the discovery of the stratosphere. Well, initially they just used kites, and with a kite you got up to 3-4 kilometers. Little factoid here. What's the altitude record for kites? How high? I should take a poll here. Anyway, I have a lot of slides, so it's 9.74 kilometers. At Lindenberg in 1919. Yeah, and still the record as of today. Yeah. Well, with 9 kilometers, you barely touch the tropopause. So in those days, they actually used what's called registering balloons, and I'll show you a picture in just a second of what the instrument looks like. So a strip chart recorder that they hang on a balloon and let it go. And if they're lucky, the instrument comes back, and then you can look at the strip chart and get a profile out of it. If the instrument is lost, sorry, no measurement. Tesseron de Bourg and Assmann, when they launched them, they quickly realized, oh, there's something funny going on in temperature profile. It's not an adiabatic temperature profile anymore. It's becoming constant or even getting warmer. And they immediately said, oh, something must be wrong with our strip chart recorder. I mean, the sun is blasting on it. It's probably radiative heating, so something must be wrong. So Assmann then, he actually went back to Alfred Berson, yeah, who did this ballooning stuff, and asked him, hey, can you do a flight in your balloon? And he actually went up 10.8 kilometers in this basket balloon. And he took readings on a thermometer while they were going up. At the same time, they flew one of those registering balloons in parallel. So redundant observations right back there. And when both profiles showed the same thing, and they were confident, oh, it's not the instrument. There's really something going on in the atmosphere. And so these two guys, they actually had an exchange of letters, and we have one of our letters in our conference room hanging. And they were discussing that, and finally in 1902 they published, hey, there's something, and they called it the stratosphere. I think it was Tesseron de Bourg that coined the term then. So here's the inauguration of the Lindenberg Observatory, and this is something I wish would happen again in today's day and age. A lot of honoraries showing up, and of course you probably wouldn't recognize them, so I highlight them. 2 heads of state, Prince Albert of Monaco and Kaiser Wilhelm of Germany. And both of them, Prince Albert of Monaco, financed several campaigns, ship campaigns, both in the Mediterranean as well as in the Atlantic, as well in East Africa from his own personal money using his own personal sailing ship. And Kaiser Wilhelm personally supported a bunch of the balloon observations. I wish something like that would happen again today, that the president personally opens an observatory with his own money. So this is how the observations looked like in those days. This is the Winch house. It's still existing today. It's a national landmark on our observatory grounds. This is the kite. Obviously not yet 9 kilometers up in the air. Typical altitudes were actually 2 to 3 kilometers, maybe 4. And they did not just use one kite, but they used up to 8 kites. So the record was done with 8 kites on the line. But it's a lot of effort. They did, over more than 30 years, on average, 2 kite profiles every day. More than some sounding sites today. So a lot of work that went on in there. Here's a picture of the Marvin Meteorograph. That's one of the very common ones that was used then in the early parts of the last century. And you have a recorder for temperature, pressure, and humidity in there. And it was just stuck in the kite there, and as the wind was going through the instrument, it would just record the profile as it was going up and down. And this is how the data then look like. You have these strip charts, and then the meteorologists have to actually make sense out of it, all by hand, drawing maps by hand. Lots of work. So a lot needed to be done to make this better. And this is why people then finally came up with, well, can we do radio transmission? And can we transmit the data down? So the radiosondes then were basically built in the late 20s and early 30s. And there's somewhat of a controversy who's really had the first radiosonde. Robert Bureau at the Trapp Observatory in Paris. He's probably the first one who launched a radiosonde, that thing on the left. That measured, however, only temperature. And Pavel Molchanov in Russia built a sonde that measured at least temperature and pressure. So maybe that's the first radiosonde. The term radiosonde comes from Robert Bureau. And Paul Duckert and Lindenberg was also one of those very early pioneers, also in 1930. So these 3 guys were probably the real big drivers of the radiosonde development. Well, here's a familiar name, also from this period. Just 5 years later, Vilho Vaisala in Finland built the Vaisala radiosonde, and we're still familiar with that name as of today. And one very interesting facet, I actually found a little schematic of how the thing works. sorry if you can't quite see it, but it's basically an RC oscillator. And you have two capacitances that vary. Basically, you have two sensors for temperature and pressure and two reference capacitances. And then this wheel would just basically commutate between those two instruments. That basic principle, that basic idea is still realized in today's RS-92. So it goes all the way back to the very first radiosonde that they did. I think just in the new radiosonde that come up now, they actually abandon or deviate from that basic principle. So it's very interesting what they did. That was a real quantum leap in the observations, because now they could really go all the way up into the stratosphere and get the data in real time and can use them in analysis. Wouldn't have to wait till the strip chart comes back by mail or by horse carriage whenever it would be found. So the next minor step change then was the invention of the ECC ozone sonde. So that was now first time that you can measure a chemical tracer on them. That was done routinely. And just in about the same time period, cryogenic frost point diagram. And I'll show you some examples at the end of the talk. So this goes back to the 70s, but I'll leave my talk mostly in the pure radiosondes, pressure, temperature, humidity. So let's jump to the present. We have now a very large observing network. And there is almost 1,000 sites, somewhat 900. It depends exactly which sites are operating. But this is the upper air observing network as of today. If I plot all of them that had delivered some radiosondes, they're probably 4 times the amount of sites, which is somewhat of a reflection that the upper air observing network is somewhat suffering. They're expensive. A lot of sites are being closed, so we'll try to make the best of it. However, one of the problems is that with all of these observations, it's hard to get a climate record out of it. So about 15 years ago, roughly, GCOS, so within WMO structure, they said, well, we should pick a small set of these sites and really make them climate-worthy sites and climate sites so we can do climate studies with it. It's a much smaller set of sites, but basically this is what comes out of it. So what this particular graph shows is specific humidity at 300 hectopascal. It's from global reanalyses. So the radiosondes go in there, but also satellites go in there. I'll show you just an example of a radiosonde in the next slide. So we have observations for 100 years. Pressure, temperature, humidity, with kites, with radiosondes going up there. We should have a feeling of how has water vapor changed. Well, let me ask you, how has water vapor changed? If you look at this graph, pick any of those lines, well, that's your answer. Which one is the correct one? Well, I don't know. Yeah. So basically, we have all of these observations, but we're unable to make a statement, how has upper tropospheric water vapor changed, at least over this 35-year, roughly, time scale. There's one reanalysis that really sticks out. It actually shows a decreasing trend. All of the others, they show somewhat of a constant, maybe slightly increasing trend, but the absolute magnitude even is not quite clear. And that's a big thing.
Excuse me, I think the vertical layer are different here. Like air's vertical layer actually is changing with the temperature itself.
That's right.
And,
that's right.
Different line actually is different layer.
That's right. That's actually from the reanalyses. It's the same layer. Airs, of course, has a weighting function on it. You're absolutely right. But the main point is, well, which one is right? So you need better observations. That's the main catch of it. So I want to show you how this looks like from one randomly picked radiosonde site in the world, just any one. Well, of course, I picked Lindenberg. This is how the same, I picked 8 kilometers. It's about the same altitude, relative humidity at 8 kilometers, how it looks like in the last 50 years. You see some nice jumps up and down. You say, oh, what happened there? There's a lot of activity going on. But if I show you the instruments that were used to measure it, the radiosondes that were used to measure it, you see a nice correlation. Here's a nice jump when they went from that sonde to that sonde. Here's a nice jump down when they went from that sonde to that sonde. It's like, well, what did the atmosphere do? And the problem is even worse. You might think, at least here, Vaisala RS-92, the current state-of-the-art radiosonde, that at least is a homogeneous data set. Well, the sad truth, it's not. because even that sonde has changed. They've changed the coating on their sensor, which directly impacts the humidity measurement. They've changed the processing algorithm and introduced some corrections that are not taken into account for here in that graph. So even though you might think that one instrument is consistent, it's actually not.
Did you do some overlap period of time and compare anything changing, and how does that go?
Thanks for looking at the cue cards I handed out earlier. I hope you others have them. You're absolutely correct. And that's one of the big things here. In fact, it's right there, I think. That last line is the answer for your question. A trend estimate from this set of observations is not possible because the trend signals are really dominated by instrumental change. And most of these instrumental changes have been instantaneous, which means no overlap. These are operational sites, and, well, people then didn't really think, oh, well, climate trends, well, it's too expensive to do. Now we see that what comes out, and that's why it's really hard to do. Those observations were done for numerical weather prediction and not for long-term climate. So because of numerical weather prediction, well, it's not that important. If there's a jump in your radiosonde, you can take care of this in the simulation stage. You do a slightly different bias correction, and then the model doesn't blow up anymore. So that's how that's been handled. And the last point, of course, if you see jumps like that, you say, well, what about calibration of these sondes? What about traceability to some sort of a standard? I mean, why are they different? And the summary statement is the measurements are not traceable. There are some systematic biases between the instruments. There are some uncertainties that are not characterized at all. And that's why it's so hard. So all of this then was the motivator to start GRUAN, GCOS Reference Upper Air Network. And it's the reference part that's really important. We want to have reference observations. GRUAN, the acronym for it, GRUAN is a ground-based network for reference upper air observations for climate. And that immediately means if we have instrumental change, we need some overlap. But I'll say some more about that. We have currently 16 sites, and our long-term goal is to expand to something like 30 to 40 sites worldwide. And so this is our map. This time I actually didn't put the GRUAN logo on here just to show you, well, we have lots of room to expand. We need sites in those areas. Nothing in South America, nothing in Africa. Reunion Island, which is actually France, is just getting into the network. We've already lost Nauru, an arm site, and Manus arm site will be closed, I think, at the end of this year. So we will lose our two main tropical sites, which is a big loss for the network. But that's how it goes. So what are the goals for GRUAN? The first thing is, of course, maintain observations for climate over decades. So we really have a long-term view. But, of course, when we get this question, well, can we do a climate trend with GRUAN data? Well, we have 5 years of data if you want to do a climate trend over 5 years. And the standard answer is, well, come back in 30 years when you have a 30-year record. So our first customer actually is not so much the climate folks who want to look at long-term trends, but more the satellite folks, so the satellite community. So one of our next goals is validation of satellite systems. And that's simply because we get this question from satellite systems. Well, how good are our measurements? Can you validate them? And how good are your measurements? And we want to provide data for NWP because that actually does help improving the models, yet so slightly. A goal, it's listed here as a goal, characterize uncertainties. It's also a tool, and you'll probably see at the end what I mean by that. It's very important to characterize the measurement uncertainties, which means the systematic biases and whatever else you have, so you can actually describe what happens when you change your sondes and what you need to do when you change from one radiosonde to the next one. Traceability to an SI unit or an accepted standard is the next thing. And I'm not going to say much about it, but that translates into some slight changes in operating procedures so that you actually can trace your sensor to some standard that hopefully you have before you launch and don't necessarily trust the manufacturer's calibration. It's important to have comprehensive metadata collection. And the reason for that is that a lot of the radiosonde data you look at today you don't know what radiosonde was flown. How was it processed? What type of radiosonde? What model? What coating was on there? A lot of this metadata, meta information is missing. In GRUAN, we definitely want to collect all of this. Because we know this is really hard. We need to validate our observations through deliberate measurement redundancy. And that's why I pointed out, the discovery of the stratosphere had this deliberate redundancy already 100 years ago. Yeah? When you measure something, you want to be sure, hey, am I really measuring the right thing? So it's good to have a second measurement. GRUAN is supposed to measure a lot of things, so we prioritized it to make it practical, and we start really with water vapor and temperature. Pressure and wind are on there as well, but because of GPS, it's not that big of an issue as of today. We're also starting with ozone as our priority 2 parameter. So, what constitutes a reference observation? GRUAN is a reference network, there's reference observations. And I'm going to take a zip here, and I'll let you answer that question. What's a reference observation? Any suggestions, please? Don't be shy. Nothing? Guys, come on. Oh, well. I'll give you the answer here. Let's move along. We actually defined really. This is our definition that we refer to when we use the term reference observation. We don't mean, oh, it's a reference gadget, that has a sticker on it or something. What we mean by reference observation, it is traceable to an SI unit or an accepted standard. So and this traceability chain means something. It actually means something in terms of operating procedures. It provides a comprehensive uncertainty analysis. And if you've ever looked at GRUAN data, you may not have, but please do. We provide a temperature profile and a vertically resolved uncertainty for this temperature. We provide a humidity profile and a vertically resolved uncertainty for this humidity. In fact, we provide 2 different types of uncertainties because it's a little bit tricky to describe it. Every parameter has a vertically resolved uncertainty. So when we get the question, well, how good is your data? Well, just look at it. It says right there. We provide you that information. We maintain all raw data, which is an important thing because we might learn something in the future where we find out, oh, what we did back then wasn't quite right. We should do it differently. Well, we can. We have the raw data. We can reprocess it again. It has to be documented in accessible literature. And in fact, how we do the processing for the Vaisala RS-92 is, I think, right now in AMT in discussion. So if you want to look it up and comment on it, you're welcome to do so. And it has to be validated by comparison or redundant observations. And there's many ways how you can actually implement this and do this. It could be dual sondes at certain schedules. It could be comparison to remote sensing. So GPS, for example, GPSRO is a possible redundant observation. Just that you convince yourself, yes, my measurement is what I think it should be. And the last, of course, include complete metadata description that we will describe in the metadata. This is how we process it. This is our version. This is the correction. This is whatever parameter is needed to describe these data. So here's a little graphical representation of that, of what we mean by that. A GRUAN measurement is the best estimate for our parameter, our temperature or humidity or pressure, whatever, plus the uncertainty, vertically resolved. How do we get there? Well, we need a traceable sensor calibration. How was the sensor calibrated in the lab? Vaisala, for example, they calibrate actually over the entire temperature range. Okay, that's good. Some other manufacturers do not. And I know one manufacturer, I'm not going to name who it is, they only calibrate at room temperature and take a standard curve down to minus 90. So is that a traceable calibration at minus 90? No. You need to know the uncertainty of your input data. And I'll show you 2 examples for that. And this is the radiation correction. During daytime, your temperature measurement has a radiation correction. Well, how good is that correction? We need to quantify this. We need to quantify the uncertainty of that correction. And it has to be a transparent processing algorithm. We need to know exactly how was it processed. And that is an issue in some of the operational systems because their processing is a black box. You don't know. That's why we actually put it on there. We don't want to have a black box. It may be in the processing, it might be in the sensor itself. But black box, if you don't know what's going on, can't be a reference. disregarded systematic effects, something we cannot tolerate. And here the Vaisala RS-92 again is a nice example. They had this radiation drybys during daytime measurements. So the sun hits the sensor, heats up the sensor is too dry. And they didn't take care of it. Well, eventually they did. Now they have it. But this is something that cannot be part of a reference measurement. And then the last thing, of course, if a manufacturer comes and says, oh, I have this great gadget and it does everything you need, but I don't tell you how it works because it's proprietary. Sorry, that's not a reference observation. You need to understand how it actually works. So here are some in situ soundings instruments that we deal with. So our core right now is the Vaisala RS-92. So we have all of this worked through with the RS-92, but we want to do the same procedure with other radiosondes, not just the RS-92. For that reason, we actually, in Lindenberg, we fly the GRUAN radiosonde as well in parallel. We fly here the Intermet radiosonde in parallel to do this. There's the CFH, the cryogenic frost point hygrometer. I'll show you some examples. Even for that, I'm working on this to get the same kind of procedure. So vertically resolved uncertainties, characterize everything that goes in there, do a ground check to ensure the traceability. It's a lot of work. Okay, so how do we determine the uncertainty of a measurement? So here's an example of the Vaisala RS-92RH measurement. The Vaisala RS-92RH is actually quite a good measurement. It's reasonably well calibrated, reasonably well, a little star and footnote. I'm not going to talk much about it. But the big thing is, any polymer sensor, any radiosonde sensor, when they get cold, they get slow. Well, in the lower troposphere, middle troposphere, that's not that much of an issue yet, but in the upper troposphere, well, the response time of that sensor goes to many tens of seconds to minutes. And at 5 meters per second, that's non-negligible. So Vaisala actually, and in our GRUAN processing, we have a time lag correction built in. Well, time lag correction, well, how is that? Here's a little formula, so how you can measure it in the lab. Time lag correction is a time constant right here. One little parameter that goes in there. We can build a correction around this. We need to measure this one. Well, actually, Vaisala gave us these numbers. Yeah, here there's a table. There's actually an old paper from Larry Milosevic when he was still here that lists those coefficients. But we said, you know what? We want to characterize the uncertainty of that. So we measured it ourselves. So we set up a little experiment in our climate chamber. This is a picture of the open climate chamber. It's very similar to the one that you have here. It's temperature control. We can go down to almost minus 80, minus 75 in that range. And we set up 2 radiosondes. Yeah, you see them there in the picture, 2 radiosondes, a dry airflow in there. We split the airflow. One airflow goes through a humidifier. And then we have here a 3-way valve. So at a constant temperature, by switching the valves, we can switch between dry and wet, which basically makes a step change. And with that step change, we can get directly at this time constant. So this is how a measurement like that looks like. Here you see the temperature profile, and this is, how much is that? Several hours. You see the temperature profile here, and this is, of course, the important region. You see a small jump in the temperature of about a degree because the temperatures are not exactly perfect, but it's close enough. And then you see here the switches between those different wet and dry airflows. And you see when it's at a warmer temperature here, it's basically just a nice rectangle. Here you already see, oh, it's kind of slow. So from this slope here, we can actually directly determine that time lag coefficient. And here's the result of that. This is our measurements. We have 2 different, we looked at 2 different steps, which means from wet to dry and from dry to wet. It's not necessarily the same. But it turns out, at least from our measurements within the statistical uncertainties, it probably is the same. There's not much of a difference. And here are the numbers we got from Vaisala, again separated by wet to dry and dry to wet. And it turns out our measurements are probably a factor of 2 slower than what Vaisala has in there. And we discussed that just a week ago with them. And said, oh, interesting. Let's look at that. So this is, now we really opened a can of worms. And that's important because if it's really as slow as we think it is, then our time lag correction has to be accordingly larger. And that will change the humidity profile in the upper troposphere quite a bit. So that's a very important thing to understand that. And it will change, of course, the uncertainties. Now, if we're not quite right, if the truth is somewhere in the middle, well, it's not a big problem for us because we have the raw data and we can reprocess our data again once we actually settled that particular issue. So here, this is how that looks now when you've gone through all this work, and there's a few other steps that I skip here. You end up with a profile that looks like this. This is a particular profile from Manus, and I show you particular Manus because it's a tropical site, very cold temperature. And then you see here, the actual measurement plus this gray shaded area is the uncertainty. It's a 1 sigma uncertainty on that particular profile. So we tell you how good is the confidence, our confidence in the observations. Down here, it's actually quite good. But the higher you go, the bigger that uncertainty gets. We tell you that. Here's another example from Lindenberg. Here, it's this gray shaded area is not quite as visible because we don't get quite as cold, and the sensor always is a little cozier. Doesn't have to work quite as hard. But I show you this example because we have a redundant observation with it. So in that particular profile, we have a cryogenic frost point hygrometer on the same balloon, measuring the exact same parameter. And now we can compare the two, and you see actually a very nice agreement throughout the entire profile. Maybe small differences here and there, but overall a nice validation of that particular measurement. If it was always like that, I would be really happy. Unfortunately, it's not, but most of the time. But the point is, here is a bad example, a different profile. Up here, we have quite a significant difference between the two sensors. And again, we showed that to Vaisala, and it was like, well, what exactly is going on? We don't know. So we need to keep an eye on this one to understand why sometimes, mostly, the agreement looks good, but not always. So the cooperation with the manufacturers is really needed to address these issues. Let me give you a second example of how we get to the uncertainties, and that's the daytime temperature of the Vaisala RS-92. And I'm not quite sure whether you've looked at the stratospheric temperatures, so you might relate to that. So again, Vaisala gives you a radiation correction table. It's just a lookup table, solar zenith angle, pressure, and add or subtract that amount, that many degrees from your temperature measurement. But how good is that? How did they come up with that? There's a classic black box. So we actually measured it ourselves. And what we do, we built a radiation pod. Here you see it open. There are two sensors in there. There's this one that is always in the shade, and then this one, which is underneath an aperture, and you actually see the aperture right there. And this aperture is closed, opened, closed, opened, and you see the same kind of step jumps as you saw in our RH experiment. And from these step jumps, we can immediately measure it. This is the radiation error. And this is the result we get from these particular measurements. So we need the pressure. So in our pressure vessel, we measure the pressure. We need the velocity. So there was a fan in there, which created the air motion. We know this one. And we need the irradiance. And the irradiance we measure. We do these experiments outside in the sun. And we have a pyranometer right next door, so we actually measure the irradiance. And those are these three parameters. And we put them together as our independent variable. And then on the left side, we see immediately here we have a jump of 1.5 degrees. This is our radiation error in the lab under these controlled conditions. How do we get to the radiation correction in flight? Well, to do this, we need to make some assumptions. And the first assumption is that on average, there's only 50% of the irradiation. What do I mean by this, 50%? Well, the way we did this experiment, we took the Vaisala sensor, and for those of you who are familiar with it, but the others, the temperature sensor is a wire. It's a lengthy device. And we always make sure that it's directly perpendicular to the sun. So we hit it full power. But when the thing flies in the air, it does this. So it might be sometimes like this, directly head on, or sometimes like this, perpendicular. Well, here you have a big radiation error. You have almost none. Well, which one is it if you average out? Well, on average, maybe 50%. That was our assumption in that particular version of the data. We also need to make an assumption on the actinic flux, so the total long wave and short wave radiation that goes into our sensor. And we get this from a streamer model. So we actually model, well, what's the diffuse upward and downward radiation, and the direct sun? Well, the direct sun, unfortunately, is the easy one. And this is what we come up with. And once we added all of this together, this is Vaisala's lookup table, and this is our particular measurement, plus the uncertainties with it. This gray shaded area gives you the uncertainty of the confidence of our radiation correction scheme. And it's quite large. And in fact, it turns out now that we just recently revisited that issue, and we actually may change that a little bit. So we are working on version 3 that may not look quite as good. But we'll see.
Yeah, I'm sorry. Can you say a little bit about how you determine your uncertainty here? This is like a 1 degree somewhere.
Exactly. So how do I get my uncertainty? Yeah. Thank you for looking at your cue card. This is it. Yeah. So what are the sources of the uncertainty? In fact, it turns out the real big one is the sensor orientation, because we don't know how the sensor rotates. It's quite large. And we actually put a video camera on the balloon to watch how does the radiosonde rotate. And it's really interesting. We thought, oh, it's spinning like crazy. It may not do anything at all for many, many seconds. It goes up just like this. It may rotate sometimes. It may not. Well, if it always like this, our assumption of 50% is wrong. We should use a full power correction. Well, maybe it's oriented like this. We shouldn't use anything at all. But we don't know. We just don't know. There's no way to get a handle on this one. So the sensor orientation is actually the largest source of the measurement of the uncertainty. The ventilation is the second one, and the ventilation refers to the ventilation in our radiation pot. When we did this experiment, we had a circular flow, and that's why I was so eager to see that wind tunnel you have downstairs. So we had just a circular pot, and how good was the ventilation in our pot? So that actually adds considerable uncertainty to that one. The radiation field, how good do we know the radiation field? Well, once we're above the cloud in the stratosphere, it's reasonably easy, except, of course, there's albedo. And the albedo might vary by quite a bit. But in the troposphere, well, I mean, you're under a thick cloud, you have no radiative effect, or you're clear sky, you have a lot. But fortunately, when in the troposphere, the radiation correction isn't that large, so it's not that big of a problem. And of course, our simple lab measurements, they have some uncertainties. There are two small factors also, and that's the ground check. Vaisala has a ground check, which is actually not a ground check, but a recalibration. And so you have to allow for some uncertainty on your reference temperature sensor in your ground check. That also goes in there. And so all of these added up, then we come up with this estimate on our uncertainties for that particular profile. So it's a lot of work and many, many little steps that go in there. So outlook. Where do we go from here? Well, GRUAN, of course, is a good thing. We really got the idea. Look at the uncertainties. Try to understand your measurements, what corrections are needed. There are certain operating procedures that you need to maintain to really be able to measure, to continue this over a long time period, even when your sensors are changing. So we work really hard on this one. But what else is out there? And one of the big things, what's happening now, is that radiosondes are getting actually quite small. So Vaisala just released their new radiosonde, which is a little less than half the weight of the RS-92. It's a little over 100 grams. It's a really small radiosonde. A Japanese manufacturer has one that's even smaller than that. And all of the other are working on making their instruments smaller. At the same time, they also allow interfacing. In fact, I have this one. They allow interfacing so you can add extra sensors and transmit other measurements down. And that's a big thing, because now we will be able to measure more parameters with just plain soundings. Radiosondes, of course, are losing their pressure sensor. That's a small little tidbit here. And that's because of GPS. You can derive the pressure from the GPS measurement. It's a cost saving, it's a weight savings. There's a little bit of a trade-off, especially in the boundary layer, where the pressure sensor is actually superior to the GPS. And another big thing that is happening is that the number of observations is decreasing, simply because soundings are expensive. A lot of sounding sites are cutting back on their frequency of observations, which means it's important that the quality of the observations must increase if we don't want to lose over the large-scale network of things. So I give you an example here, and that's something that we've started in Boulder. Emra sits back there. We've done that in Lindenberg quite extensively. At a number of other sites where we actually fly not just a radiosonde, but we fly a frost point hygrometer, we fly an ECC ozone sonde, the same one. In Lindenberg, we actually fly a Cobald Backscatter sonde once a night as well. We fly a second or sometimes even a third radiosonde in the same balloon. And there's a wealth of observations, of data coming out of this. And if you're ever interested in analyzing it, let me know. I'll send you the data. We need people who actually analyze all of this stuff. So here's just a little, and this is now a stratosphere example, and just because I think it's fascinating, it's interesting, and some actually real interesting science. And Emrys, I'll talk to you about this afterwards. This is an observation from 2011. This was the first one on 3rd of June that I saw. This is from Beltsville, so just outside of Washington, D.C. It's a cryogenic frost point hygrometer profile that they've launched as part of a LiDAR validation campaign. And they've had a good number of other soundings before that. And just for reference, I plotted all the other profiles they have just on top of it. And what you see there is one profile that sticks out like this. And for anybody who's ever looked at stratospheric water vapor knows it's pretty boring. It's a straight line and not much happening. So when you see a thing like this, it's like, oh, what's going on there? Well, initially we thought, oh, it's a fluke, nothing to worry about, it'll go away, don't worry about it. 3 weeks later, in Lindenberg, we see this. It's like, oh, again this fluke, that's interesting, maybe there's something to that. At 23 kilometers altitude, so here in Lindenberg, we're 13 kilometers above the tropopause. To see a bump in water vapor like this is quite unusual. And this in the middle of June, when it's supposed to be the most boring of them all. And I call up my colleague in Finland and say, hey, do you want to launch one? And it took him another week, and he launched one, and he has one that sticks out a little bit over there. So there was something going on in there. Well, 2011, it didn't impact you quite as badly, but the Europeans definitely remembered it. They remembered it better from 2010. There was a volcano there. Icelandic volcano, it's the second one. It's Grimsvötn, which erupted on 22nd of May, 2011. There's an actual picture of the eruption. I think that's within, I don't know, half an hour after the eruption. It wasn't a big volcano in the big scale of things. Few airports were closed in northern England, I guess Scandinavia a little bit. Not as big as the one in 2010 that closed most of Central Europe. And within a week, this one had stopped, so not a lot of people paid attention to that. But I quickly realized, like, oh, in June there is this water vapor thing, and a few weeks earlier there was this volcano. Maybe that has something to do with it. So I contacted the Icelandic Met Office, and I say, hey, what do you know about this volcano? And they sent me this picture of, or this data of plume top altitudes. So they have a lot of volcanoes blown up, so they actually set up for that. And they could send me two sets of data. One is their C-band weather radar from the airport. And another one was actually a mobile radar that they moved much closer to the volcano to actually look at how high does the volcano go. And it turns out the initial eruption definitely went up to 20 kilometers, and with one little blip up at 25 kilometers. So there was a very short burst that actually went really high. But it didn't last very long. And then the altitude came down 15 kilometers for maybe another 12, 24 hours. And then most of it was 10, 8, 6 kilometers, and then eventually stopped. So the very initial volcanic eruption went really high. So, well, next step I did was, well, let's look at the trajectories. And this is now trajectories at constant potential temperature, and I just did two different groups of trajectories, 490 to 540 K. This is the lower altitude. This is the altitude where they saw this blip in Beltsville. And then the gray one, 560 to 610, that's at altitude where we saw that water vapor layer at Lindenberg. And it turns out there's a nice correlation. The lower altitude actually went all the way south, went a little bit west and then bent south all the way into the US. And so there's a nice correlation. If water vapor made it into the stratosphere, that would be very consistent with these trajectories into Beltsville. Into Lindenberg, the same thing, except it goes once around the pole. That's why it took 3 weeks until we saw the signal. And so we see Lindenberg here, Sodankila there, and they just saw a little bit left over from that. So there's a nice correlation. Hey, this is probably volcanic. But do we have any other information about the volcano? And it turns out we do, because we were really lucky. This one single observation, that little bump, was one of those where we got multiple sensors on it. We had a backscatter sound on there, and we had an ozone sound on there. And now we can really look at it. Here, the green one, that's the ozone profile. And what you nicely see, there's a little bump, a little negative anomaly in the ozone. And that's a clear indication that air most likely came from down below, not from up high. If the air had descended, where you actually do have more water vapor, you should have had more ozone. But we don't. We have less ozone. Well, the next thing, what about backscatter? Do we see any particles? And here it gets really interesting. Here the red curve and the blue curve is backscatter signal at 940 nanometers in infrared and 440 nanometers in the blue. We don't see any backscatter signal there. There's no aerosols in there. So this is a pure water vapor signal, most likely emitted from the volcano and just shot up there. So the sloppy term for that one, it was a wet volcanic flatulence. Just one shot up there, it deposited some water, it made it all the way to Beltsville, once around to Lindenberg and Sodankila, and a very interesting thing. So have we understood what volcanoes do to stratospheric water vapor? Maybe, maybe not. Fortunately, not too many volcanoes go off in the stratosphere all the time. The last real big one, of course, Pinatubo in '91. But our observational capabilities weren't quite as good back then as they are now today. So it was just a nice little outlook example of what can be done when you have multiple instruments on the same balloon. And there's lots of little developments going on that will allow us to combine different instruments on sounding balloons and measure in the atmosphere. So, I had one more. Because we do this routinely, once a month, backscatter measurements, just wanted to show you. This is at the blue wavelengths and left at the infrared wavelengths. But important part is all these profiles here on the left are before that eruption. All those profiles here are in the 6 months following the eruption, which means there was actually a volcanic signal. But the volcanic signal, in terms of aerosols, only made it to maybe 15 or 18 kilometers, not to up here where we saw the water vapor layer. And again, that's consistent. Yeah, the volcanic ash actually is settling down slowly, so we keep observing it, and it was actually distributed over the entire northern hemisphere. But on the big scheme of things, not a very large eruption. So with this, I end here. Summary: for more than 100 years, in situ observations were largely taken for numeric weather prediction and process studies. That is expected to change, and in situ observations are expanded into climate observations right now. In situ observations can be used as reference observations. And when I use reference, please have that definition in the back of your head that I listed up there. This is one of the big strengths of in situ observations over remote sensing observations. Reference observation means, of course, uncertainty plus traceability plus raw data plus metadata. All of this you must have in place if you want to call an observation a reference observation. And then, of course, technical advance allows the combination of instruments and opening for a new way of using soundings. Thank you very much.
Thanks, Holger. We have time for some questions.
I don't understand one statement you made, and that was the substitution of quality of the radiosonde soundings for frequency. I mean, you really don't average radiosonde soundings together, do you? So I don't understand how the quality is really a substitute for frequency.
Actually, very often you do. If monthly means, for example.
Oh, okay.
Oh, very simple one.
I was just thinking more of application to a particular weather forecast. But yeah, that's a good example.
Monthly means the prime one. And there, for example, it's very important. In Cobald, for example, the GRUAN site, they went to twice daily to once daily is one of those examples. And we discussed which ones should they cut. And fortunately, they cut the daytime observation, that they continue the nighttime observation, because there you don't have this radiation issue.
All right.
So you actually improve the quality overall a little bit.
Hey, Holger, can you expand a little bit on how the CFH, your CFH instrument, can be used as a reference, and what some of the pitfalls or possibilities of using that instrument as a reference?
I didn't explain that, but for exactly that reason, I put the uncertainty estimate on here. And in that case, actually, I put a 2 sigma uncertainty in there. And it's a whole different talk to explain how I get to the uncertainties. But the good thing about the frost point hygrometers is it's based on a very good physical principle. So you just have to look at, well, what are the little pitfalls that happen? And one is calibration of your sensor, your temperature sensor, because ultimately it's just a temperature measurement. And the second one, how good is your controller? These are the 2 main limiting things. And ultimately, this is what comes out, especially for nighttime soundings. The uncertainty is actually quite small, and that's what makes it into a reference observation.
Is the CFH, I guess, immune from the radiation measurements, since it's sort of covered?
Principally, yes and no, both at the same time. It's different for the NOAA. I think the NOAA is not quite as light sensitive as the CFH is. So in daytime measurements, I could have shown you an example. The uncertainty is quite a bit larger than that one. And that's because the controller of it sees the sunlight, and then introduces oscillations. So the trace doesn't look quite as clean. It becomes a lot noisier. But the good thing is, it's just random noise. There's no bias introduced by that one. So your uncertainty gets increased as a noise term, not as a systematic bias. Systematic offsets are just determined by your calibration, nothing else. So I'm happy to explain you much more in detail. So give me an hour or 2.
Clearly, some of the GRUAN sites have the capacity to do much more measurements than others. But can you say briefly what is the baseline for the different sites as far as what they need to have, or is that something you showed and I missed?
That is a very, very good question, and like all good questions, it's a very difficult question. Let me get back to our map here. I have it somewhere. There. Of course, you have Lindenberg here, which has lots of capabilities. Payern, Cobald have lots of capabilities. So, if you want to offer me a GRUAN site in between there, your bar is very high. You need to offer a lot of additional capabilities. At most of these sites, we have LiDARs, we have microwave profilers, we have infrared, and I don't know, and we can launch all sorts of sounding equipment. So we have a very high bar if you want to add a new GRUAN site there. You want to offer me a GRUAN site there? I'll take almost anything. So the bar there will be very low. But low just in the kinds of observations you do. There is no compromise on the operating procedures and the quality of the observations that you do. So we're working right now here with Galapagos, for example, or Costa Rica. I would like to get their operational radiosondes into GRUAN. And our bare bone minimum requirement is, well, you do regular soundings at least once daily. Hopefully they get a redundant sonde in there, and in Galapagos it's doable because of the ozone sonde program, and a GPS integrated water vapor. And the GPS integrated water vapor, that's your redundant measurement, at least for the column water vapor. And if you can convince them, and there's one more requirement, and that's an additional ground check. But that's basically it. So it's relatively small, and we would patch a big hole in there. So it really depends on how much value a site adds to the network, and so somewhat flexible.
I was just wondering if you've heard of any long-term issues with the supply of helium. I've read some places that the strategic reserve of helium and the price of it is really...
well, we changed from hydrogen to helium 3 years ago, and for safety reasons, obviously, even though we have a very well-maintained and very safe hydrogen operation. But it was, interestingly enough, cost savings measure, even though helium is more expensive. I think about a month after we'd switched over, we get a letter from our supplier saying, oh, you know, there's a shortage of helium and we're not quite sure whether we can deliver you the gas you need. It's like, oh, thank you. It's an issue. Yeah. It's definitely an issue, and I think it will remain a big issue. The U.S. politics has a big role, especially because of the strategic helium reserve. So I think because they flooded the market out, they've kept the prices really low, so there's a lot of use there. And eventually the reserve is depleted and suddenly there's no supply anymore. And then it will become quite prohibitively expensive. So sites that can fly in hydrogen safely, they're well advised to continue doing so. But it's non-trivial to fly using hydrogen.
Hi, could you comment on the difference between in-cloud measurement and clear sky measurement? For example, is icing going to be an issue, or is there any way to mitigate the icing?
In-cloud and out-of-cloud measurement depends on which sensor and what parameter you want to look at. Temperature measurement in cloud, my guess, is probably not terribly impacted. Even though the sensor ices over, it's probably still at thermal equilibrium, so you should get a good temperature measurement. I might lean a little bit far out the window here. But there, the issue is once you get out of the cloud, you have a iced over sensor, and now they have the evaporating cooling effect, and you actually get quite a significant cold bias coming out of the cloud. For humidity, of course, it's different. Your humidity sensor ices over. That's the reason why Vaisala has two sensors. They actually heat and measure alternatively. With that method, of course, you're much less sensitive to cloud icing issues. But you still need to be aware of that this is happening that way, because detecting cloud top is still tricky, because one sensor that's measuring still ices over in the cloud. It comes out of the cloud, it's still iced over. And that may last for another minute or so until they switch over to the dry one. So there are things like that. For the CFH, it's not an issue unless it's a really wet cloud. A really wet cloud, then the instrument gets completely soaked and then it's dead. But you know when it's dead.
Okay, I had a big question, which is there a room for UAVs, UASs in reference radiosonde measurements?
What do you mean by reference observation?
Traceability.
So basically, the way we've designed it, it's actually not limited to soundings. Absolutely, if you have an instrument on a UAV that you can characterize in the same way, hey, why not? In fact, a UAV, I mean, I can easily imagine some nice examples where you have a UAV flying near a balloon. If you want to use this as a validation observation, for example. So yes, absolutely, it should be possible. But of course, you will have to deal with some of the UAV-specific issues that you don't have on a balloon.
Well, if there are no other questions, I think we'll thank Holger again.
Okay, thank you.